back into section 6 of chapter 10, and we're going to look at a couple more examples here where we're going to be graphing plane curves, but our plane curves are given in terms of parameters. We have parametric equations that are given. Now in the previous example, the one from the last video, there was a restriction on what time could equal. If I'm not mistaken, I think it was t was defined between -4 and 4. But if there is no time interval given for t, we just assume that it can be any number as long as x is defined and y is defined for those values of t. So in my next example, you'll notice here that x is equal to the parametric equation, x is equal to the square root of t minus 1. Well, we would know right away there's restriction on t because you can't have a negative number under the radical, so that would mean that t would have to be greater than or equal to 1. And over here, there is no restriction on t at all. But this is enough to make sure that when I pick the values and I set up my double t chart, that I am picking values that make sense when I plug them into the parametric equation. So it says in the first part here, a little different than the last example, it says eliminate the parameter and write the equation in rectangular coordinates. Now, what they want us to do here is kind of go back from parametric equations to what the original equation would be in rectangular coordinates. So that means we have to eliminate t. Now there's a couple ways that we go about to eliminate t. I might take this first equation, x is equal to the square root of t minus 1, square both sides. I would get x squared is equal to t minus 1, add 1 to both sides, and I would get t is equal to x squared plus 1. Then I could make a substitution of this expression in for t over here. So what that would do is it would give me y equals t, which would be x squared plus 1, minus 1. And so this gives me y equals x squared. And we know that that guy, and I lost my TV reception here. What the heck is going on here? All right. Come on back. Now let's see what happens here. Anyway, that would give me the equation of what appears to be a parabola. But remember, we have a restriction. T has to be greater than or equal to 1. And that restriction affects x, because that would mean that x would have to be positive. And if x is positive, we don't have an entire parabola that opens upward, vertex at 0, 0. But instead, we would have only when x is positive, so we would have only in the first quadrant, that part of the graph. Now, we can see that by creating the double t-chart, which I don't think I've left myself enough room for. I'm going to have to write awfully small. I'm not sure where my logic was here. So t, and then x, and then y. And remember, x has to be greater than or equal to 1. I am going to start with 1, because if I plug 1 in, I get 0 and I get 0. So my first point is going to be right here. And that kind of makes sense because that's a parabola with vertex at 0, 0. You know that from your quadratic function days. Now, if I plug a number like, well, in this case, I'll probably go ahead and plug 2 in. But if I plugged in a number like 3, I'm going to get the square root of 2. And now I'm not dealing with nice, neat integers anymore. So I'm going to pick 2 because that will give me a 1 here. And then I would probably pick 5, because 5 minus 1 is 4, and that works out. And I'd probably pick 10, and I might even pick 17, and that hopefully will give me more than enough. I did set up my scale a little bit to include some tall y values there by setting the scale for the y-axis at 2. So I'm plugging these numbers in so that I get integers for x. If I plug 2 in, 2 minus 1 is 1, the square root of 1 is 1, and if I plug 2 in here, I get 1. So that's this point right here. And then I plug 5 in. 5 minus 1 is 4. The square root of 4 is 2. 5 minus 1 is 4. So I have 2, 4. And you're hopefully starting to see what I was talking about before being just on the right side here of the parabola. I'll plug 10 in. 10 minus 1 is 9. The square root of 9 is 3. 10 minus 1 is 9, so I have 3, 9. So that would be 3, 4, 6, 8, 9. Let's see. 3, 9, that'd be about here. Hopefully, yeah, that still kind of looks like my parabola here. And then if I plug 17 in, I don't think I need to plug in too many more than this. 17 minus 1 is 16. The square root of 16 is 4. 17 minus 1 is 16 here. So 4 is 16. Let's see, this is 10, 12, 14. This is 16 here. So 4, you probably can't see it very well with my frame in front of it there, but that would be my points. And my curve would go, oops, I missed a little bit, and it would go up like this, and the orientation would be in this direction. Now again, notice here that it's not a complete parabola like this one says, because there was the restriction here on the parameter. So you're going to have to keep track of that if you change it to rectangular coordinates. Don't just graph this because this is looking familiar. Be careful, okay? Now, the parameter t comes into play most of the time because t usually represents time, as I was talking about with the example of the spider and the fly, where they cross at 0, 2, all depending on at what times, so that we knew if the fly was going to avoid being caught by the spider. Well, in this next example, I have a different parameter. I have theta, and you'll see this happen quite a bit with trig functions. And what we're going to do here is very similar to what we just did. We're going to first take this pair of parametric equations. We're going to eliminate the parameter, and we're going to write the equation in rectangular form. But then we're going to graph it using a double T chart and graphing the points there, even though the equation that we get in part A is going to look pretty familiar, I believe. So I'm going to write down that x equals 4 cosine theta and y equals negative 4 sine theta, and I'm thinking, well, do I have to like divide by 4, take the inverse cosine, or divide by negative 4, take the inverse sine? Well, I know this. I know that from a previous chapter on trigonometry, we know that cosine squared of an angle plus sine squared of that angle is equal to 1. So what I'm going to do is I'm going to think of that as making this substitution here. In for cosine, I'm going to write this, the cosine of theta is equal to x over 4. And over here, the sine of theta is equal to y over negative 4. And then I'm going to take those guys and plug it into this Pythagorean identity. So this is going to give me x over 4 quantity squared plus y over negative 4 quantity squared is equal to 1. Well, this is x squared over 16 plus y squared over 16 equals 1, or better known to its friends as x squared plus y squared equals 16 if I multiply both sides by 16. And as I mentioned, we know what that is. That's a circle with center 0, 0 and radius 4. So let's see if we get that sketch by plugging in some values here. I'm going to make a double T chart like I said before. And I'm going to have theta, and then I'm going to have x, and I'm going to have y. And I want some angles that are easy to plug in. Well, if my angles for these trig functions, which are periodic, my angles would make most sense if I kept them from, say, 0 to 360 or 0 to 2 pi if you're doing radians. So I might go say, oh, I don't know, 0 pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then back to 2 pi, which hopefully gets me right back to where I started, which kind of makes sense since it's a circle. If I plug 0 in, the cosine of 0 is 1, so this is 4. The sine of 0 is 0, so this is 0, 0. So my first point here is right here. Now, didn't we say that it was center 0, 0 and radius 4? It's matching up kind of nicely. If I plug pi over 4 in, the cosine of pi over 4 is the square root of 2 over 2 times 4 is 2 square roots of 2. The sine of pi over 4 is square root of 2 over 2 times negative 4 is negative 2 square roots of 2. So it's not going counterclockwise. This one is going to go clockwise. 2 square root of 2, about 2.8. 2.8. Okay. At pi over 2, the sine of pi over 2 is 1, or excuse me, is 0, times 4 is 0. The sine of pi over 2 is 1 times negative 4 is negative 4. So now I'm graphing 0, negative 4. 1, 2, 3, 4. It's right here. Do you see how my circle is going clockwise? So far anyway. I plugged 3 pi over 4 in. The cosine of 3 pi over 4 is negative square root 2 over 2 times 4 is negative 2 square roots of 2. And if I plug 3 pi over 4 in for the sine, that's positive square root 2 over 2 times negative 4 is negative 2 square roots of 2. So we have third quadrant. So about 2.8, negative 2.8 by negative 2.8, be about there. And then if I plug in pi, the cosine of pi is negative 1 times 4 is negative 4. The sine of pi is 0, so that's just 0. And that puts me right here, 1, 2, 3, 4. Really looking like it's going to be a circle with center 0, 0 and radius 4. And I continue this process. So 5 pi over 4, that's going to be negative, so that's negative 2 square roots of 2. That's going to be negative square roots of 2, but that's positive because you're going to multiply it by 4, so that's 2 square roots of 2. So about negative 2.8, 2.8. About like that. And then 3 pi over 2, the cosine of 3 pi over 2 is 0, so 4 times 0 is 0. The sine of 3 pi over 2 is negative 1 times negative 4 is 4. 1, 2, 3, 4. And 2 to go. 7 pi over 4. I plug that in. Cosine of 7 pi over 4 would be square root 2 over 2 times 4 is 2 square roots of 2. And then if I plug 7 pi over 4 in, that's negative square root 2 over 2 times negative 4 is also positive 2 square roots of 2. I like it when it comes into play here. And as you might guess, when you plug in 2 pi, you'll get the same values as you do when you plug in 0, because these are coterminal angles, and you are back at 4, 0. So it kind of goes, now my circle connecting the dots is not going to be very good. My points are pretty good for once. Yeah, this is going to end up looking probably more like an ellipse. And I'll go ahead and I'll put the orientation in. Turned out it was, as I mentioned, clockwise. Now it says sketch the curve and indicate the orientation. Well, I did that there, and I did that down here as well. Alright, so we have more things to look at on plane curves and parametric equations, but we're off to a good start. So let's see what happens here in the next video.